Okay, so I think we can start. Welcome everybody. So in this sector, let me start by thanking the organizers for this for the invitation to present this set of 3 lectures, and the idea for this cycle of presentation is to illustrate a bit some techniques that allow us to extract information from scattering amplitudes, and that tell us about the properties of classical gravitational, in particular binary systems. We may think in particular having in mind to massive objects that we send in some masses and that initially have some velocities and interact. So let's say they have some relative separation scale r, and well, this is of course a very old problem. It's in a sense the two-body problem in gravity, and our objective in these lectures is to well try to see what happens when we send in these two objects, and in particular we will be interested in information concerning their dynamics. So by how much, for instance, they deflect when feeling each other's interaction. So, for instance, one observable we will discuss in this lecture is the so-called deflection angle. Another interesting observable, of course, especially in view of the fact that our experimental colleagues have become increasingly good at it, is the gravitational waveform. So, while deflecting, these bodies, of course, emit gravitational waves. And interferometry experiments like LIGO, Virgo, Kagra, associated experiments, and also in the future new experiments are planned for the coming decades, such as the LISA, Einstein telescope, have put in place interferometry experiments that actually measure the gravitational waveforms that are emitted by these kind of systems. And well, since this is after all a workshop on infrared physics and BMS and asymptotic symmetries and connections to celestial holography, we will put in particular emphasis on properties of this gravitational wave spectrum. Say that the gravitational wave spectrum is characterized by some frequency omega, properties that have to do with the soft limit, so the regime in which omega is very small. So I'm working on some lecture notes which might appear at some point in the future, but for the moment, let me refer you for most of the material that I will present to this review written together with Paolo Di Vecchia, Rodolfo Russo, and Gabriele Veneziano, which you can find on the archive, as published in Physics Report, and which focuses in particular on one particular angle that allows us to perform this connection that I will try to describe from scattering amplitudes to these classical systems, which goes under the name of iconal exponentiation. So this is, in a sense, the topic of this first lecture. And so we will. The idea for this set of lectures is to start from a simplified setup in which we can focus really just on the dynamics of the two objects by neglecting radiation, and then little by little, also depending on how I'm doing with time, we'll introduce dissipative effects, which are to do with the emission of radiation starting from the soft limit, which is also interesting due to its connection with BMS. And later on, if time permits, I will try to discuss how one goes beyond this soft limit, and one can actually produce predictions for the gravitational waveforms as well as for other quantities such as the total emitted energy, the total emitted angular momentum, also beyond the soft limit. So, by the way, let me emphasize that I warmly invite you to ask questions all the time. We can make this as interactive as possible. It's not needed that I really fill the last bullet point here completely. Okay, so let me start very generally just by some words of introduction and motivation, just to set the stage for the ensuing discussion, to bring everybody on the same page. So, as I said, this is our system that we want to study. Say these guys have masses m1 and m2. In these lectures, we will focus on the case in which these two objects are scalars, so they don't have intrinsic spin, although a lot of literature has, of course, focused also on the inclusion of spin effects, as well as further effects related to the internal structure of these objects. But for the moment, let me study the spinless case. So, of course, this is, in general relativity, this is a complicated problem because these objects interact with the gravitational field, which obeys highly nonlinear field equations, and well, these are notoriously hard to solve. So there can be two possible mindsets to approach this problem. One is to, well, put it on a computer, right? So this has been the effort of numerical relativity, which is very important. So let's say approach 1. Numerical relativity. Instead, in these lectures, we will try to focus on a different angle of attack, which is, let's say, approach 2. Find a small parameter and do some perturbation theory. So we can find a small parameter, we can expand the problem in a regime in which it becomes treatable analytically. So analytical approximation methods. So I wanted to start just by reviewing some of the approximation methods that have been used to study this problem, also to establish a bit the terminology that we will use in the rest. So one, which is perhaps the most famous and time-honored and developed one, is the so-called post-Newtonian, or PN. And this is an approximation which expands simultaneously in a regime of weak fields, or more precisely, in a regime in which the typical size of these objects would be 2gm over c squared. Say the Schwarzschild radius is very small compared to the typical separation, and simultaneously of slow motions or non-relativistic speeds. So this is really also the one which is studied in all GR courses in order to check that your gravitational field far away reproduces the Poisson equation for the gravitational potential, for instance. This one? Yeah, it's an R, sorry. Calligraphic R, maybe prefer this one. Okay. Yeah, so this is very well realized, in particular for binary systems which move on quasi-circular orbits. So this is in fact the most common type of binary systems that are observed at interferometry experiments, in which the two objects orbit around each other by staying very far away. Since they are on circular orbits, essentially the Virial theorem, or well, in layman terms, the fact that the gravitational pull must provide a centripetal force for the circular orbits fixes these two quantities to be of the same order, and therefore they must be small and of the same order, which allows one to apply the post-Newtonian approximation to begin with. So just to have an idea, these parameters are order of, let's say, 1/10 in typical, for instance, for the first one that was observed back in 2015, these are relatively small, so then you can use them to produce a perturbation theory around them. The approach which we will focus on in most of these lectures instead is so-called this post-Minkowskian, or PN. Unfortunately, these two letters M and N are almost unintelligible when I say them, so please ask me if there is any confusion at any point. This is a bit different in the sense that one expands indeed still in a regime in which the two bodies are still far apart, so they interact weakly. However, it stays agnostic compared with respect to their velocities. So in this sense, it's a relativistic approximation scheme. In fact, the velocities can be arbitrary up to, let's say, a caveat, which we will hopefully discuss in the next lecture if I manage to get there. So let me say that the velocities are generic rather than really arbitrary. We'll come back to this point. But just to have a first idea, this is the picture one can have. And then maybe couple of words on the relation between these two approximation schemes. Of course, in principle, they are distinct. However, in fact, I have still some space here. Let me use this. So one important point is that, of course, when two different calculations have been done in these two different regimes, they can be compared because one can re-expand both in their common regime of validity. Which is, of course, Gm over R squared, much smaller than V squared over C squared, much smaller than 1. So in other words, you can re-expand any Pm expanded object for small velocities and any Pn expanded object for small gravitational interactions. and the two results must agree, otherwise it means that one of the two collaborations has made a mistake. So this seems obvious, but it's actually very useful, since, as we will see, these two sets of results have been developed by sort of entirely different communities. So oftentimes performing these checks actually tells you something, allows you to understand something new. Yeah. It's a bit more subtle than that, because as you can see, there is a hierarchy of scales. Maybe it becomes even a bit clearer if I reorder my equations like this. Oops. So as you can see, what happens in the actual post-Newtonian expansion is that you have some objects expanded in some parameter which sometimes people call eta squared, which is of the same order as these two guys, and it is a non-trivial function of gm over v squared over times r, right? This ratio is of order 1. So for instance, a very simple example I will come back to later is the thing we all learn in undergrad, which is the scattering angle for the Kepler problem. And if you go back, you will find that it is an arc sine of precisely this ratio, gm over, okay, b, the impact parameter, times the velocity squared. So it's an arc sine, it's a nonlinear function, right? Instead, the post-Minkowskian approximation is systematically expanded in g, m over r squared. So in particular, the leading order quantity that we will calculate, this deflection angle, we will derive hopefully in the next few minutes, will be g times something, but it's an expanded function in g. That something is a non-trivial function of the velocity, though, which is relativistic. So a priori, in order to compare one with the other, you have to take the Newtonian one you learn in undergrad and expand it for small g, then the arc sine just becomes its argument plus corrections, and expand this one for small velocity. So that is why I'm speaking about the common regime of validity. However, I will not discuss them in the lectures, but there are techniques to actually give some post-Minkowskian data, perform a partial resummation, essentially, and go back to the full PN result at the first few orders in PN. Yeah. Very good. So this is the type of approximation schemes that one can define even just in GR, right? Up to now, I haven't been speaking about amplitudes and quantum effects at all. However, what we will do in this lecture is something that may seem at first a bit cumbersome and unnecessary, but as I said, we will start from quantum scattering amplitudes as we formulate them in quantum field theory, and then take the classical limits. So let me be precise about that. We will consider a classical PM regime, which means that, okay, we have to discuss another length scale. There is not only this GM, so the classical size of the objects, and R, their separation, but there is an additional scale, which is, say, the Compton wavelength, possibly times some factors of pi. And we will stay in a regime in which this Compton wavelength of this object is very small compared to the other two scales in the problem. So in particular, we will consider a classical PM scattering regime, just because we want to use scattering amplitudes. Although, as I said, most of the, essentially all of the observed events are actually mergers, not scatterings, but okay, for today you have to stick with me and do scattering. So these parameters sizing the separation will be the initial impact parameter, say B, Bj, and then these guys will fly off to infinity. So the hierarchy of scales we will consider is this one, where, to reiterate, this is what allows us to stay in the PM regime. As I said, this could be order 1 over 10, roughly speaking, just to have an idea. If one plugs in the values that are valid for typical binaries in the initial in spiral phase, when they are still very far apart. And this is instead, so this is PM. And this is instead what we mean by classical limit. So, put another way, gm squared over h bar, probably with some factor of c, should be very big, right? So another way of stating this classical regime is that the mass of these objects should be trans-Planckian, right? It should be much bigger than the Planck mass. And in fact, if you try to plug in values as an exercise, you will find that this parameter is of order 10 to the 79. If you put in the masses of the black holes that were involved, for instance, in the first observed gravitational wave signal, which means that indeed the classical approximation is very well satisfied, of course. Okay. And then maybe a couple of words on other limits in which we can expand, which are in a sense orthogonal to what I just said. One of us is our soft limit. So in general, we would like to let the frequency stay, so omega frequency. For typical gravitational wave spectra emitted by systems of this type, the frequency is roughly of order V over B. So generic. However, we can go in the soft limit, which means, in this case, omega B divided by B very small. And this is an approximation that we do on our signal, right? There is a whole spectrum of the signal that in principle is observed. Say, this is, for instance, the energy emitted as a function of frequency, for instance. The soft limit only captures what happens here and doesn't tell you, in principle, anything about the rest. And then another approximation that is also useful in particular because next generation experiments such as LISA will be particularly sensitive to these types of mergers is instead the so-called extreme mass ratio limit. So we will stay in a regime in which the masses are generic. Particular, they could be of the same order, one slightly bigger than the other or not, equal masses. However, one can go in the extreme mass ratio, which is, say, M1 much bigger than M2. Or, as people sometimes prefer to phrase it, one introduces a so-called symmetric mass ratio parameter, M1, M2 divided by the total mass squared. And then in this regime, this is very small. So-called extreme mass ratio. This is, yeah, the symmetric mass ratio. And yeah, the physical meaning of this approximation is that one expands in a regime in which one of the two objects is much heavier than the other one. So the heavy, to leading order, the heavy guy simply sits there and does nothing, and the light object just moves along the geodesic of the geometry sourced by the heavy one. So this is the familiar probe limit that we all study also in undergrad, like for instance, when studying geodesic around Schwarzschild. And then people have developed a systematic framework to go beyond, which goes under the name of self-force formalism. So maybe just to give you some keywords in case you are curious about what you read sometimes on the archive. Okay, so this was more or less my general introduction, just to give the broad picture. And then for the rest of today's lecture, instead, we are going to focus on this specific regime here, and try to learn about our gravitational wave observable in this regime from amplitudes. Are there any questions on the sort of general philosophy? Please. Exactly. So as I was mentioning at the beginning, the best possible approximation scheme really for mergers that move in which the systems move on quasi-circular orbits is the post-Newtonian one, precisely because you have this virial theorem, or equivalence between gravitational pull and centripetal force, and therefore you expand in more parameters, so it gives you a sort of a better analytic approximation for those kinds. However, the PN regime fares slightly worse for highly elliptic orbits, and it's not applicable for hyperbolic motions at high velocities. So in this sense, there is some interest, although at the moment not yet experimentally, for looking also at scatterings. Although I have to say now that the data is becoming more and more plentiful, by now hundreds of, tens of events have been collected, and experimental collaborations, provide some guidelines for what they should do next, and they started including also, looking for more exotic types of systems, including possibly captures, so systems in which the two objects were initially unbound, but then they capture each other, and then also perhaps scatterings. So this is one motivation for trying to expand a bit our toolbox to go in that other direction. Another possible reason of interest is that some of the results that we will discuss for scatterings can be analytically continued to the bound case. I will, again, not really discuss much that, but it goes a bit in the direction of what I was answering earlier to Yannick, because some of the techniques that allow us to partially resum, to go from PM to PN also are related to continuing some of the quantities. An example, just to have an idea, this deflection angle that we will discuss, you can analytically continue it to calculate the precession angle for motion along a elliptic orbit, quasi-elliptic orbit. Yep. That's right. That's right. As long as you stay in low orders in which you don't really see any back reaction from the emission of radiation, it doesn't really make much sense to speak of soft approximation, because there is no radiation of which one can take the soft limit. Yeah, in a sense, it's a bit different from the other limits, in the sense that the other limits are properties of the binary systems, right? We either take them to be far or close, or have heavy mass, light mass. This is a thing that we do. As observers sitting far away, we can just say, okay, there is a complicated gravitational wave signal that comes, God knows where it comes from, but maybe soft theorems can tell me something about the zero frequency part that I observe, and I don't know how to predict the rest. It's more something the observer restricts to, rather than a intrinsic property of the binary. Yeah. Sort of a philosophical difference, I guess. Anyway, by the way, just to advertise a little bit, as I'm sure most of you know, one important feature of this soft limit is that, in fact, also of the other limit here, is that it does not rely on the post-Newtonian and post-Minkowskian one. So it can produce predictions that are valid also for strong gravitational interactions. It doesn't care, right, about the fact that the gravitational system could be strongly interacting or not. So this will be one useful feature for us. Okay, so now that this sort of more general part is dealt with, unfortunately I have to start with some sort of slightly boring aspects about kinematics and conventions that I will use. So we will work in a Lorentz invariant way, and this ties very much with this idea of staying for generic velocities. So one key point to remember is that it's sort of natural that one can try to find a connection between scattering amplitudes and this PM regime, because as you can see, the power counting parameter here that allows us to check at which order in perturbation theory we are is precisely G, which is the gravitational coupling, and this will be the same coupling that appears in our gravitational amplitudes. And another idea is that staying at generic velocities means to be Lorentz invariant, and amplitudes are naturally Lorentz invariant. So what I wanted to start with is just specifying my conventions for the metric, and then sometimes we will stay in dimensional regularization to tame some infrared divergences that appear at intermediate steps. So D is going to be slightly away from 4. I'm going to use the following normalization for one particle states. Which is the relativistic invariant one. And, well, our key object, as I'm sure you're all familiar with from your undergrad courses on quantum field theory, is the S matrix, which is just the time-ordered exponential of I over h bar, the integral over the interaction Lagrangian density, and is conventionally expanded as 1 plus I, the so-called T matrix, and amplitudes are the T matrix elements. So for some initial and final states alpha and beta, the matrix element T alpha beta in momentum space will be given by a delta function that encodes the conservation of momentum for momentum or the momentum times what we call the amplitude. So this calligraphic A for me. Okay, and the useful thing about you introducing this decomposition is that once you have stripped off this 1 and this delta function, the amplitude is supposed to be a function, not a distribution. And to start with, just to start from the possible simple setup that has something to teach us about the problem we are interested in, we are gonna focus on on the simplest possible amplitude that encodes information about our two-body system, which is a 2-to-2 amplitude, which I will sometimes denote with. In terms of that notation, alpha going to beta would be P1, P2 going to P3, P4, or sometimes I will denote with a blob, and this would be 1, 2, 3, and 4. Or sometimes I will simplify a bit the notation and just call it A of S and T, which I'll demand as time invariants, which I'll define in a second, or sometimes even further simplify to alpha A of Q. I will define everything in just a second. So for me, this will be the guy with mass M1, and this will be the guy with mass M2. So P1 squared plus M1 squared is equal to Z, and similar for P4 squared, etc., etc. Similar here for P2, P3 with mass M2. And the Mendes time invariant S is minus the incoming momenta, so P1, P2 squared, or equally, of course, the outgoing ones for the elastic process. And of course, if you square this explicitly, you find M1 squared plus M2 squared plus the double product in which there appears this P1 dot P2, for which I'm introducing a notation. This is going to be called sigma for historical reasons, although, of course, this is what, well, normal people would call the gamma parameter. This is the Lorentz gamma, as defined in, say, is the Lorentz, this would be the velocity as defined in the rest frame of particle 1, this would be the velocity of particle 2, or vice versa. This I leave you as an exercise to check. So with this notation, this is going to be 2m1 m2 sigma plus m2 squared, or gamma if you prefer. And well, since we are already speaking about boring conventions, let me also remind you one standard fact about relativistic 2-to-2 kinematics, which is the fact that you can always choose a reference frame called the center of mass frame, which is special because the momenta... by the way, I will take a convention in which all momenta are regarded as outgoing, but of course this simply means that the incoming momenta P1 and P2 are actually minus the physical momenta of particle 1 and particle 2. So, okay. So the center of mass is special in the sense that total spatial momentum is 0. And then what happens is that during the scattering, no energy exchange happens in this frame. So P4 is equal to E1 P prime, and P3 is equal to E2, the same E1 and E2 that you see here, minus P1 prime, sorry, P prime. So this is really the picture that I was drawing here, right? This would be P, this would be P prime, this would be minus P, and this would be minus P prime. They have the same length, they are just rotated by our angle theta. And our first objective will be to come up with an approximation for this angle theta in the post-Minkowskian regime. And another identity that you can show as an exercise is the fact that the magnitude of this P, so the spatial momentum in the center of mass frame, and the total energy, which is, by the way, the square root of this Mendes time invariant S, are related. Sorry. The energy is the square root of S, are related by this identity. P times E equal to M1, M2 square root of sigma squared minus 1. This is just a convenient, nice identity that sometimes we will use. Very good. Where should I erase? Probably there. And the last piece of sort of kinematic notation that I need is think this chalk is becoming a bit too short. Let's try this one. So in order to simplify a bit the notation, let me define a symbol for the phase space delta functions as these guys, the mass shell delta functions associated to the final states, P3 and P4. Let me call it Lorentz invariant phase space 3, 4, which is just the product of the two pi theta 3, 0. So this is the Heaviside theta function, by the way. P4 plus and 1 squared. And the useful thing about this object is that I can use it in this way and define the S matrix element for the 2, 2, 2 process in a sort of nicer way. So if you take this thing and use the definition in terms of 1 plus IT and the normalization of the one particle states, you find that this is just a delta function which you can strip off. Times what I'm calling the S of the 2 to 2 process, which is just 2 pi delta of Q, Q being the momentum transfer. Sorry, I forgot to define that. I promised I would do that, but then I forgot. So this small q is just the momentum that is exchanged from particle 1 to particle 2. So you see, since my conventions are a bit weird, in which P1 is minus P1, this would be P4 minus P1. So P1 plus P4 is the momentum that is that goes from particle 2 to particle 1, plus I 2 pi delta of 2P1 dot Q 2 pi delta of 2P2 plus Q times the amplitude. Okay, so this is all just boring kinematics. Apologies for this, but sometimes it's needed. Okay, so this would be the object from which we want to learn something about our deflection angle. So let's try to see how that goes. Perhaps I can erase over there. So the first point is that in this hierarchy of scales that I'm just erasing, unfortunately, we are in position space, as you can see, right? There is this B. Instead, our amplitude is in momentum space. But of course, we all know what we should do in this case. We should perform a Fourier transform, right? So the first thing is to go from momentum space, from Q space to B space, or impact parameter space. And yeah, the idea is just to literally take a Fourier transform, so no surprise there. With respect to the impact parameter, with respect to the transfer momentum, sorry. So the idea is, of course, that the impact parameter and then the transfer momentum are dual to each other, right? This is sort of intuitive, as when taking processes at larger impact parameter, the transfer momentum decreases, right? Because the things interact less strongly and therefore deflect less, and vice versa. So let me, for the moment, just define this quantity. And as you can see now, after having done all these gymnastics with the delta function, it sort of pays off, because the first term over there, just by definition, gives 1, plus this Fourier transform of the amplitude A times those two delta functions. So let me introduce another symbol for that, ft of A, which is now a function of B. And this is just going to be the integral and then we will discuss what these two delta functions actually mean physically. Okay. So physically, this means that the Fourier transform must be performed while keeping the masses of the final states the right ones, right? These delta functions just came by enforcing that the final states still have masses m1 and m2. And then, to start with, let me recall that we are not interested in learning about the full amplitude, right? We are only interested about learning about the classical limit, and more precisely, in fact, let me rewrite it somewhere, about this regime in which h bar over m is much smaller than gm, and they're both much smaller than b. And via Fourier transform, of course, b is just of the order h bar over q, right? So large b translates to very small q, right? And this means in this Fourier transform, to leading order, I can simply neglect these q squared with respect to q and q here, right? So to leading order, let me define this simplified Fourier transform a e to the I b dot q. And now the meaning of this relation is very simple, right? It simply means that we are taking not a d-dimensional, but a d minus 2 dimensional Fourier transform in the plane orthogonal to p1 and p2. So if we really picture the scattering as in the center of mass frame, we are taking the Fourier transform in the plane orthogonal to the incoming velocity. So it's a two-dimensional Fourier transform. In fact, as an exercise, you can show that if you go in the center of mass frame, this frame we have defined over there, you can recast this a tilde. Yeah. Right, I see what you mean. I guess the logic I'm trying to push here is a bit the opposite, right? Since we're only interested in the regime in which these two objects stay very far apart, so B is very large, we are only interested in learning about, in taking the region of this integral in which Q is very small, which is in a sense a soft limit, but here Q is really the momentum transfer of the gravitons that are exchanged. In fact, the objective now will be to actually calculate the leading order for this amplitude, which is the single graviton exchange. So Q would be literally the momentum exchanged by this single graviton, which is soft, but it's also off-shell, right? Because it's just an, so yeah, I will reserve the term soft for on-shell gravitons that are emitted, I guess, yeah. Very good. So if you go in the center of mass frame, you can check, I mean, let's say it's an exercise, that this is 1 over 4 EP integral over the d minus 2 dimensional perp components of AQ perp e to the I b dot q perp, where, okay, q perp is, let's say, the tie-aligned momenta in the last direction. This is what I mean by q perp. Well, okay, here will be longitudinal components that are set to 0 by these two delta functions when you do the exercise. And remember, by that identity, you can also rewrite this prefactor. It was 1 over 4 m1 m2 square root of sigma squared minus 1, as you prefer. Okay, very good. This is for you to check as an exercise. So, okay, this was in a sense still all kinematics. We will discuss how we actually learn from this procedure by doing an example in a moment. I just wanted to provide you, in case you want to reproduce more in detail some of the calculations that I will show later, the basic type of this Fourier transform that we need to take when dealing with this 2 to 2 amplitude. So typically, these Fourier transforms are not hard for the 2 to 2 process because, as we will see in a second, the amplitude here is just a function of the type q squared or q perp squared to some power, and these Fourier transforms are all known. And you can calculate them, for instance, introducing Schwinger. So if you want to take the Fourier transform of this kind of function, the result is the following. B squared 1 plus nu minus epsilon. Okay, this is if you want another exercise. Notice here a nice feature of this Fourier transform that as we were saying, we can focus to leading order on the regime which Q is very small. So this is what allows us to go from here to here, and in fact also expand Q for small q, A of Q for small q, as we will see in a second. But there is a bit more than that, right? In particular, we are only interested in a regime in which B is large, which means that we are only interested in things that are actually non-zero for large B. This sounds a bit trivial, but in fact, it's actually useful because it means we can also neglect anything in this A of Q which goes like, say, Q squared squared, or is independent of Q, right? Because it would give rise to a delta function. Suppose here, right, you don't have anything. This would simply be the delta function of B. So its support is at B equal to 0. And similar if you have Q squared. So this formula should tell you that you don't find anything when this nu is a positive integer. And indeed, you see that this precisely gives 0 for nu a positive integer. So this is actually a general mechanism. So to summarize, we only care about non-analytic Q-square dependence because analytic terms like Q squared to the n, say 0, 1, blah, 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 they would become delta function with some, possibly with some derivatives of delta function, which are local. So we can ignore them. So in a sense, this goes back to, for instance, ideas that you might have heard if you had a look at these papers by Donoghue, for instance, back in the days, in which they were calculating effects in the gravitational potential that have to do with treating gravity as an effective field theory, which you might worry is not a well-defined thing, because as UV divergences, these are very complicated, and we don't know how to renormalize them. But this is a mechanism in which we recover a well-defined prediction for large distances, so in the IR. And the reason is simply that we don't care about anything that is local in momentum space, which is analytic in momentum space, which would translate to things local in position space. And all the issues about gravity as a non-renormalizable theory, etc., at least at low orders in perturbation theory, are all sitting in these terms that we don't care about. Okay. Very good. So I think yeah. Right. So there are two possible answers. One is that, as we will see, it gives the right result. So in a sense, okay, but it's not the answer you want, of course. No, there is a more systematic way. I don't know if I will have time to introduce it, but the idea is to start really by preparing to wave packets far in the past, which are separated by some impact parameter which you give a name to from the beginning, and then set up the problem, and then you will find that indeed, essentially what happens is that the impact parameter, what you have to do is that you have to separate them by performing a translation from one to the other, which introduces this e to the I b dot q, and when you sandwich, for instance, an observable, which could be the deflection angle or any other observable in this in these two in states and act with the S matrix, this translates exactly to this impact parameter Fourier transform. But in general, so at leading order, everything is very simple to check. At next to leading order, there are some subtleties. Maybe I will come back to those, but yeah, this is the idea that was introduced by Kosover, maybe O'Connell. So it's a sort of alternative way of performing the connection with respect to the iconal, which I'm focusing on here. Maybe if I have time, I will come back to it at the end of this lecture, at the beginning of the next. Very good. So let me now finally use it, all this machinery, to do something, instead of just presenting some kinematical identities and results. So let me start from the simplest possible application of all this philosophy, which is the scattering of two massive spinless objects that are minimally coupled to general relativity. So literally the simplest, I think, possible setup. So these two guys interact with some Lagrangian, which I will maybe write down just for completeness. This will be the Einstein-Hilbert part, and then we have two two copies of a massive scalar field. Plus the mass. Then I finished my space. And this should be it. So let me not go through the full detail of the derivation of the Feynman rules, but just maybe list them. This is textbook material after all. So we write down the Feynman rules in the Donder gauge. So in particular, the gravitational propagator is something like this. There is a matrix here that I'm gonna write down in a second, divided by, say, this is a function of k, then this will be k squared minus I0. Yeah, this is sort of unfamiliar because most of textbook presentations of quantum theory are in mostly minus signature. So usually one speaks about the plus I epsilon prescription of Feynman. Okay, here it's going to be the minus I epsilon prescription just because I've changed the signature. And P is this guy. So this is the graviton propagator. Then we have the scalar propagator, which of course we take not to change the flavor. Let's say we have labels 1 and 2 with some sort of flavor labels. Plus ma squared minus I0. So this is just the... So. And finally, I guess I need the vertex to build the first non-trivial example, and the vertex is this one, which I'm going to call tau minus I kappa p mu p prime nu plus p nu p prime mu minus eta mu nu p dot p prime minus m squared. And by the way, kappa is going to be a shorthand notation for the square root of 8 pi g, Newton constant. There we go. Okay, so let me use this Feynman rule to do the only calculation with Feynman rules that I'm able to do, which is this 3-level single graviton exchange. So we are going to take a bottom-up approach, right? We know we want to extract information from amplitudes. We are starting with a 3-level amplitude, which for our 2-to-2 process is just this guy. Okay, so let's see if we manage to do that. Please help me in case I write something completely wrong. So let me start from the top. So I have a minus I kappa from the vertex over there, and then I'm going to need to do P1, P4, right? So P1 mu P4 nu plus P1 nu P4 mu minus eta mu nu P1 dot P4 minus M1 squared, right? Because the mass of the particles sitting in this line here is M1. Then I have the propagator. The propagator has another minus I. Ooh, I think an I is missing here. An I from the numerator, and then I have this tensor eta mu rho, eta nu sigma plus eta. Okay, I can just, since these two vertices will be symmetric, I can simply avoid putting this 1/2 and neglect one of these two terms. So this is going to be minus 1 over d minus 2 eta mu nu eta rho sigma, and then times the vertex down below, which instead involves P2 and P3, right? So P2 plus P2 sigma P3 rho minus eta rho sigma P2 dot P3 minus M2 squared. Okay, and then I have to remember that our objective is to calculate the T matrix elements, which have this I in front of, you remember, 1 plus IT. Whereas the Feynman diagrams calculate the S matrix with the I. So basically we have to multiply by an extra minus I in order to get the T matrix element. So at least the sign should be plus, minus I to the fourth. So that's good. And then kappa to the second power, which is linear in G. So starting in the right way. And then in order to simplify my life a little bit, let me remind you of, okay, and then there is the 1 over q squared over propagator, which I forgot. Sorry. So let me remind you this observation that is still over there. We don't care about anything in the amplitude, which is analytic in q squared. So in particular, if we see that any of these contractions, let's say in the numerator, would produce anything like q squared or q squared to some higher integer power, this would cancel this 1 over q squared, right? And therefore would give a contribution that doesn't depend on q squared, or worse, goes like q squared to the first power, q squared to the second power. So let's see, for instance, this guy over here would be P1 dot P4, which is Q minus P1, minus M1 squared. So P1 squared is minus M1 squared, so this cancels with this M squared. And then you have P1 dot Q. And then you can check using the fact that P1 plus P4 is equal to, that they're both equal to minus M1 squared. So this is just a small calculation. 1 dot Q is actually 1 over squared, is Q squared. So this is 1/2 Q squared. Sorry, I'm doing things a bit in a disorderly manner, but I hope this is clear. So this term, for instance, is proportional to Q squared, right? And we can just throw it away. The same happens for the guys involving, for the terms involving P2 and P3. And by these very same identities, you can check that anything that would produce a contraction like, so anything, suppose I expand P4 as Q minus P1, and I take into account the term that comes with the Q here, then with this contraction, it will either contract a P2, and then the same identity will give another Q squared, and similarly for all the other terms. So what happens is that to leading order, and actually to lead to exactly in this, to calculate the non-analytic term, I can simply approximate here P4 with minus P1, and here P3 with minus P2. Okay, so now the only thing left to calculate is the coefficient. Let me see. So there are 2 terms here and 2 terms here. So again, I'm guessing a factor of 4. Let's see if that works out. P1 dot P2 squared minus 1 over D minus 2. P1 squared, P2 squared. Right, these are just the contractions. So this eta structure, I say, would contract P1 with P2 and P1 with P2, whereas this other one would contract P1 with P1 and P2 with P2, right? So this should be the right thing, times 1 over Q squared. Let's got things right. So times 8, 32, yeah. And then in order to use actually that definition of sigma, which I maybe erased, let me recall it over here. So here I can pull out some factors of the masses and define sigma squared minus 1 over D minus 2. Let's see if we got this right. Yeah, amazing, yeah. Okay, so this is our amplitude. And now we can plug it in our Fourier transform, use that identity over there, and find our first result for this A tilde, and then we discuss it. In fact, since I had a bit of space here, let me just directly do it here. So this would be what I'm calling A0, the 3-level amplitude in momentum space. Now I plug it in this Fourier transform and I calculate a tilde 0, the B space amplitude, and the result is the following. Well, in fact, let me include a factor of I for later convenience. 2I, G, M1, M2. Right, and let me remind you that we are working in D equal 4 minus 2 epsilon. So this is why this epsilon appears. Okay, so let's stare at this result for a second. You remember, we are calculating this 1 plus ft, which to leading order we can approximate as 1 plus I a tilde 0, which is this guy over here. And then if we are doing something sensible, we would expect that since we are doing perturbation theory, right, 3 level, and then we will do 1 loop, 2 loops, etc., this should be a small quantity, right? It should be a small expansion, a small correction with respect to the 1 that appears over there, right? However, let's look at it. As you can see, let's pretend that now we can set epsilon to 0 just for a second, just for our dimension counting. This is proportional to gm squared over h bar, which is 10 to the 80. So, okay, not very small. What is going wrong? Okay, what is going wrong is that these masses are so large that the gravitational coupling, the effective gravitational coupling is not small, right? It's gm squared over h bar. So in a sense, this is telling us that we have to throw perturbation theory into the garbage bin and do something else, maybe enjoy the nice sun outside. However, we are not allowed to do that, so let's try to go on. Pretend we are not discouraged by this observation, and we go on. And so then, of course, as I was sort of advertising, now I will no longer be able to do all the calculations by showing them to you on the blackboard, but I will try to discuss how we can calculate the one loop and then draw some lesson that is telling us what is going on and what we should do in order to restore some usefulness to this calculation. I keep finding only shorter and shorter pieces of chalk. At some point I will have to write with my nails. Okay, so suppose we are not discouraged and we want to try to go to one loop. This would be the 3-level right result. And by the way, yeah, I was mentioning we are pretending that we are in D equal 4, but this is not okay, right? Because here we have a gamma of minus epsilon, which is telling us that this result is actually infrared divergence precisely in D equal 4. As you see, this is not a problem for our application later on, but this is actually a well-known fact. It's due to the fact that in D equal 4, gravity is a long-range force, and therefore the two particles accumulate a sort of, I mean, an interaction that goes on well in the far past and well in the far future. But as we will see, the important bit is that if we expand now for small epsilon, the 1 over epsilon bit is B independent. Is B independent. So it's really just a constant in impact parameter. This will play a role later on. But for the moment, I invite you to trust me, although this seems like a bit of a desperate effort, and let's try to go on and do one loop. So at one loop, okay, in principle, the problem is straightforward. It just takes a lot of time and work. You just sit down, write all the Feynman rules, and evaluate the integrals that you have, and you find your answer. However, of course, this is not the right way to approach the problem, because otherwise, why bother using amplitudes? Things become very, very complicated. It doesn't make much sense to calculate the full quantum amplitude and then take its classical limit at the very end in order to calculate something that is classical. So there are two things that simplify our life. So one is to use a principle called generalized unitarity. So this is a very, I mean, in hindsight, a very simple idea, as often happens. Suppose you were able to calculate the full sum of all the Feynman diagrams. Okay, this is actually a very complicated task, but suppose you're able to do it. Of course, the result you will have is a complicated rational function of all the momenta of the problem, including the external momenta, P1, P2, and Q, say, and the loop momentum that you now have at one loop. Say, we call it L. Now, what happens is that it's a rational function, so you can take residues of this rational function. In particular, you can take residues associated to possible intermediate channels going on shell. So, for instance, we can take what is called a cut, or a generalized unitarity cut, which is associated to the two-loop amplitude in which these two intermediate graviton exchanges go on shell. Say we call them L1, Q1 and Q2, for instance, in analogy with our Q at 3 level. Sorry, P2, P3. Of course, the result will diverge, but the coefficient of this divergent must be the product of two lower order amplitude, which in our case are just 3-level amplitudes, that are describing this sub-process, the process in which a graviton sort of scatters against the massive object, which are, well, we can think of them as gravitational analogs of the Compton process, right? In which, well, in electromagnetism, a photon will scatter off a charged particle. Here it's the gravitational analog of that, which is, well, more complicated, but in principle has the same philosophy. So this amplitude is actually a 3-level amplitude, so we simplified the problem a little bit, and let me write it down for you because it will be a sort of a building block for what I'm gonna say next. So this is the expression, maybe. Okay, maybe to be consistent, let me define the Q going up. This is the result. Also, this amplitude is not very easy to calculate, but okay, it's still better than doing the one loop calculation directly. I can tell you more about how Q1.Q2, and then there is some structure. Let me give it a name: gamma, rho alpha, K1, Q1, Q2, gamma of sigma beta, K1, Q1, Q2, and this gamma is minus K1 plus Q1 alpha K1 rho divided by K1 dot Q2, sorry, dot Q1 plus eta rho alpha. There we go. So this is an on-shell amplitude. So we really took this one loop amplitude and then took the residue. So now effectively in each coefficient of these two guys, Q1 and Q squared are 0, because otherwise they would cancel this 1 over Q squared propagator, so they wouldn't contribute to the pole, right? So this is the building block that we can just glue together. So we can glue together one for the lower half and another one in which we replace, you know, all the labels and use for the upper blob, and glue together with some with 2 copies of this the Donder propagator that I think I wrote somewhere and then I erased. And the reason is the following: that this amplitude, so let me give it a name. Also, besides the blob, let me also give it a proper mathematical symbol, alpha, beta, rho, sigma. And the reason is that this amplitude satisfies an important property, namely the fact that whenever you saturate one of these indices with one of the graviton momenta, so in particular Q1 rho, for instance, see, and similarly for sigma, of course, you get 0 on shell, and similarly for Q2 alpha. So this is an important property which is sometimes called word identity or gauge invariance, etc. This is important because suppose you now were to contract this amplitude with an external polarization, And then this polarization would transform, as you know, under Lorentz transformation, would have a nice piece and a not so nice piece, which is proportional to this graviton momenta. But this not so nice piece cancels in this amplitude precisely thanks to this property, and therefore it makes the contracted amplitude Lorentz invariant and gauge invariant in this sense. For us, however, today this is just a simplifying property. You can find a form of this Compton amplitude which satisfies this property, and the reason why it's important is the fact that, as I was saying, this philosophy of generalized unitarity is telling you that when you take the residue at the pole, the amplitude should factorize as the sum over all the possible exchanges of massless particles in this channel. In principle, you don't know. You cannot select the positive helicity, the negative helicity graviton. They just all come together, right? Because the Feynman rules just tell you to sum over all of them. And in principle, therefore, you would be required to calculate this. So you would need to calculate the sum over positive helicity and negative helicity of a, let's say, up. Let me not write down in full glory, but let's say the one associated to the upper blob, alpha, beta, rho, sigma, and alpha, beta, alpha prime, beta prime, rho sigma, rho prime, sigma prime, alpha c, so AC, alpha prime, rho prime, sigma prime, pardon, sorry, alpha prime, beta prime, rho prime, sigma prime, down, times the poles, 1 over q squared, 1 over. So this would be the cut. However, this sum over, maybe one of them is starred. So this sum over polarization states admits a simple expression. So let me call it capital pi. Probably I should have 2 copies of these guys. Apologies for that. So one of these guys is going to be alpha, beta, rho, sigma, and it can be actually broken down into pieces as follows. Alpha, beta, rho, sigma, and then a factor of 2. So you see, this is really reminiscent of the form of this the Donder propagator we had earlier, but alpha, but each of these pi's between this is not eta alpha beta, is eta alpha beta plus an additional object that you need in order to have this transverse traceless projection over physical polarizations. K beta plus lambda beta k alpha, where lambda satisfies lambda dot k equal to -1, k squared is equal to 0, of course, and lambda squared is equal to 0. I mean, these are all a bunch of detail, but what I wanted to tell you is that the reason why you can replace the sum over physical polarizations with a simple contraction with this with P, the guy that only depends on the etas, is because they satisfy this this word identity. This is a sort of a technical detail. You can pretend this Blackboard never happened and nothing is going to happen, but okay, it was just to tell you why this condition is important. The second simplifying feature is that, in principle, in order to reconstruct the full integrand, so you know, this complicated rational function that comes from the sum over all the Feynman diagrams, we cannot just consider one cut, right? We have to consider many cuts. We have to sort of slice the amplitude in several possible channels. This would be the T channel, then there would be the S channel, and there would be, in particular, several invariants. But the important bit that again saves our life is the fact that we only need to care about things that are non-analytic in Q squared. And you can check, this is the only cut that has this non-analytic behavior. So let's say generalized unitarity, sum over all cuts, schematically. And then the second simplifying feature is that we only need one cut at this order. This one. So in principle, I mean, here I was a bit confused, I realized, but this is the only ingredient that you need to glue into this one to reproduce the amplitude we need. And then finally, maybe let me erase over there. The only another ingredient that we are left with is, of course, to evaluate the loop integral, which is still not completely obvious. What I thought to do right now was to sort of just say some words and then maybe come back to techniques to evaluate the integral later on if I have some time. Probably I won't because I don't have really a lot of time, but I think just to give an idea. So the third step would be to evaluate the L integral, so the one loop integral that we have. So yeah. Yeah, I realize. So in principle, you would need to slice the process in different ways. For instance, you could slice it in this way, or you could slice it in more refined way, etc., like this. In principle, you have to write down a complicated linear system that involves all the cuts. I mean, a so-called set of spanning cuts. You need to need enough of them in order to reconstruct the full thing. But you can check that since the other cuts would also cut some other massive lines. For instance, suppose one combination that is not captured by the cut we drew over there would be something which the two massive lines touch. For instance, suppose it's something. I don't know, it's not the vertex that we include in our theory, but suppose it's something like this, right? This is not captured because, I mean, you don't have enough propagators to cut, right? There is no massive lines here, graviton lines here. However, you can check that this does not have the 1/q² pore. And I mean, also intuitively, right, the two massive lines touch. So this is a process we don't care about because our two massive lines are always gonna stay very far apart from each other. So this is reflected in this analytic property I was mentioning, and we just throw it away. There is another subtlety, since we already discussing that. A more proper way to discuss all of this is to introduce a concept of topology. So even the Compton amplitude, you can first separate it out in terms of topologies, which are things that only have one denominator. So you can separate it out in this form in particular. So this is just a manipulation that you do on this expression I gave you upstairs, in which in particular you see several denominators appear. You can separate it out analytically into terms that only have the 1/q1.q2 propagator. So this would be the T-channel topology. Terms that only have this k1.q1 propagator, which would be the S-channel topology. And then things that only have the other one, which would be the U topology, for instance. And then you can check what happens when you glue two of those in this sort of way that I sketched here. So let's try to do that. You would have one copy of this and one copy from above. And then you just literally have to do all these contractions that I mentioned over there. So from this you will get this, and from this you would get this guy. From this you will get another copy of this guy, because we can just freely twist these two endpoints here. From this you will get this. From this you would get the box. From this you would get this crossed box. From this we can also get this because of the twisting that we can freely apply here. From this we get another crossed box. And from the cross we get another box, right? Because we can untwist the two lines. And now so now let me defer this discussion of the integrals then. And now suppose you want to do the same putatively for the one loop. Okay, in principle it's again just an algebraic problem. You have a complicated rational function, you want to separate out the contributions that have certain sets of denominators. For instance, here we'd have this denominator associated to this pole, to this propagator, and to these two, etc., etc. And in principle, you will need many topologies, but the topologies that you need for the one loop amplitude are precisely the ones I've drawn here, right? Because all the other ones you can think of do not have these I mean, have these two lines touching, so you don't need them for our long-range effects. So the upshot I'm trying to say is that this one loop amplitude will be just the sum over this plus this plus this plus this plus, well, 1/2 because of kinematic conventions, symmetry conventions, plus things that are localized, things that don't have, that don't give, let's say, 1 over q squared to some power, because the two lines touch. And as you can see, we did the job, right? Gluing two copies of this guy did exactly what we wanted, except for a factor of 2. Because we see that each of the topology is appearing twice in this table. So the more precise statement is that we don't need to calculate that guy, we need to calculate that guy and divide it by 2. Okay, this is a detail I plan to skip, but since there was a question, I think this gives a sort of more systematic idea, right? In principle, you have to do this topology decomposition for both the 3-level guys and the 1-loop guys, and then you can just list all of the topologies that you have, and be sure to match them with enough cuts, so enough gluing of lower point amplitudes that the two, so that the two sets can be inverted in terms of one of the other. This is a very simple example in which the set is exactly the same except for a factor of 2. More generally, you have to consider more cuts. Yeah. Okay, so maybe let me skip the remark about doing the integrals. Suppose we did the integrals. Maybe later on I will give some more details. And then let me tell you the result, since we only have a few minutes left. The result is the following. Well, quite generally, you can always say that the amplitude has a real part and an imaginary part. You know, the imaginary part comes from the I epsilons in the propagators and shows up when you actually do the integrals. For instance, this guy will give also an imaginary contributions. And in fact, this imaginary part is a bit simpler because it is actually related precisely to another cut, which is contained in the one we consider. Let me discuss this one later. So for this one, you have to do the calculation. So this guy is equal to, you have to do the calculation I show there and do the integrals. And this is 2 pi g squared, 1 squared and 2 squared, m1 plus m2 times 3 pi sigma squared minus 1 over square root of q squared. So it is non-analytic in q squared as promised. And then in principle, you'd have other orders, let's say plus order epsilon. I wrote down the result in epsilon equals 0, so d equals 4. But at one loop, it's actually simple to stay generic and do things in d dimensions. And now let me come back to this imaginary part. This is another story which is a bit confusing because it has a name similar to this generalized unitarity, but it's different conceptually. It's the imaginary part is fixed by unitarity in the strict sense, or if you want, by the generalized optical theorem. So let me tell you how this goes. Now forget everything I said about the integrand and let's think about the amplitude, the integrated amplitude, which comes from the S matrix. So the S matrix must be unitary, which means that if you expand it as 1 plus IT, you get a constraint on the T matrix. And then you can take matrix elements of this identity to find constraints among amplitudes. So in particular, we take our 3, 4, 1, 2 matrix element. We see that this simply gives the imaginary part of the 2, 2, 2 amplitude times a factor of 2. And this is equal to, well, here in order to make sense of this, we have to insert a completeness relation and then sum over all the possible intermediate processes that we can have. To leading order, we will have this process, which we only insert a 2, 2, 2, sorry, a two-body intermediate state. And then there will be higher order processes, for instance, this one maybe we will mention in the next lecture, but today it's not needed. And what happens at leading order in G is that we can simply neglect this guy, right? Because by power counting, you remember the leading order to the 2 amplitude would have a power of g, so g times g, which is g squared. This is exactly the order at which we want to do things right now. This guy instead would have g cube, starts at g cube. So neglected for the moment, twice the imaginary part of is precisely this. So by this symbol, what we mean here is something more compared to those topology diagrams here. They should be kept different. Here what we mean is we literally take the 2 amplitudes, we multiply together, and we integrate over the intermediate phase space. So in this case, the 2 particle phase space. That was instead a statement about the unintegrated, or so sometimes called integrands. Instead here is a statement about integrals, if you want. So this was to justify this writing here. So what I'm trying to say is that the 1 loop amplitude has a simple piece, which is the imaginary part, which you can actually deduce from the 3-level calculation we did, let's say, half an hour ago. And the real part is a bit more complicated, because for that one you have to actually construct the integrand and do the integrals. Otherwise, you cannot calculate it from lower order bits. Okay, to draw the thing to the conclusion, I still have to evaluate this guy for you, right? I only sketched how to calculate this one. This one is actually a bit simpler, and so let's try to do it on the blackboard. Maybe I can try to erase this piece. So let's write down explicitly at least once this particle cut. So by this we mean the I over 2, the integral over the intermediate phase space. Let me give an orientation here and call, for instance, this momentum L minus P1. So this would be the integral d L over 2 pi, and then the delta functions associated to the mass shell. So 2 pi, in principle there would be a theta function, but for a reason that will be apparent in a second, it's really not needed. Plus L squared, A of L, which is the momentum flowing in this amplitude, and here is instead Q minus L. Okay, the reason why the theta function is not needed is that, again, we have to remember that we don't want to calculate this thing for generic Q. We only want to calculate it for small q. And the right thing, in order to retain the non-analytic in Q behavior, is to also expand for Q, for L, in the region in which L is of order Q, and they are much smaller, say, than the masses and the energies. So what we're going to do to leading order is to simply neglect this L squared, much like we neglected the Q squares in the Fourier transform. You remember, this is exactly the same thing. So then we can take the Fourier transform and realize that this is nothing but a convolution, right? So you have the integral of A of L, A of Q minus L, and L is integrated. So what happens, and you can check as an exercise, that the Fourier transform, in particular to leading order, this tilde Fourier transform, diagonalizes this convolution. So in other words, we apply the theorem in the sense that the Fourier transform of the convolution is the product of Fourier transforms, right? So this is just I over 2, the Fourier transform of the 3-level amplitude squared, which is, oh, sorry, here the tilde dropped, which to leading order is exactly this tilde, A tilde 0 that we had, plus subleading orders that we don't care about. Okay, so so this imaginary part at one loop is actually very simple, because if you go to B space, so you take the Fourier transform that we actually need to discuss our two-body problem, it factorizes as the product of the 2 lower order amplitudes. So to summarize, let's put together the imaginary part and the real part and take the Fourier transform, and we get the following result. So A tilde 1, now the 1 loop amplitude, is the guy over there, Fourier transform. You can apply the formula that I wrote down on the blackboard a few minutes ago. And for that, so we find this guy, which is IA tilde 0 squared divided by 2. and maybe to make it even more suggestive, let me say factorial, plus this object here, 3 pi g squared, m1, m2, divided by 4 h bar b, square root of sigma squared minus 1, and then the famous 5 sigma squared minus 1, which we also had here, plus higher orders. Okay, so these are the two results that I wanted to discuss before the break. So let me remind you, we just calculated the trivial level amplitude, took it Fourier transform, and found that it's very big, gm squared over h bar. Then we calculated the one loop amplitude, hoping that we understand this problem about the perturbation theory, and what we find that it's even bigger. It's actually the square of the big one plus a correction. The good news is that the correction is not so big, because as you can see, it's proportional to gm squared times a gm over b, right? Just as a scaling. This is gm squared squared, and this was instead gm squared. This is gm squared times gm over b. So maybe there is a sense in which we can, make, we can go back to give a meaning to perturbation theory, but we have to understand the structure that is appearing here. And I'm sure several of you have guessed by now, the structure is an exponential. So what the sort of main message of this lecture is that this calculation that we did suggests, and this in fact can be proven systematically in perturbation theory for the two objects that we are dealing with in this lecture, that we can introduce a symbol, say, called 2 delta 0, this a tilde 0 over there, and then introduce a symbol for this guy over here. Let's call it 2 delta 1. And then the structure becomes the following: 1 plus I a tilde, 0 plus a tilde 1. Putting together the two results that we have is equal to 1 plus 2i delta 0 plus, sorry, I think I have to put an I over here, plus 2i delta 0 squared plus 2i delta 1. And let's say, okay, the non-trivial bit is to show that the pattern goes on, and in fact this exponentiates as e to the 2i delta 0 plus 2i delta 1. And then there will be higher orders here, and in principle there can also be contributions that don't exponentiate, but for the moment let me stick to the discussion of these two guys. And these are called the leading order iconal phase. So this is non-trivial, and has been actually shown in a paper by Kabat and Ortiz. Maybe if I manage, well, later I will write on the blackboard the archive number. Let me not do it now in order not to get it wrong. So this is good news in the sense that the take-home message is that the perturbative amplitude doesn't make sense. So for gm squared much bigger than 1, or gm squared over h bar much bigger than 1, because this is big and this is even bigger and everything keeps getting bigger and bigger. But this makes sense. It simply means that the amplitude is dominated by a large phase, by the exponential of a large phase, which is sort of I times the classical action, plus corrections. And as I emphasized, this classical action is very big, so the exponential oscillates very rapidly, but then the first correction to it oscillates a bit less rapidly. So essentially the schematic form is e to the gm squared times 1 plus gm over b plus higher order correction. So this is very big, but this is relatively small, is our PM parameter. Okay, so the bottom line is that perturbative calculation makes sense. It's just that we have to exponentiate it. So maybe before concluding, this is a sort of nice piece of theoretical information. This is a nice structure that you find in the amplitude, but our objective was not really to understand, or not just to understand the amplitude, but really to calculate some observable. This is actually very easy. The idea is that since now in impact parameter space, this quantity is exponentiated, we can take its inverse Fourier transform. So we take the inverse Fourier back to momentum space of this exponentiated amplitude e to the 2I delta. So let me give it a name. And then, since this amplitude is very rapidly is very rapidly oscillating, we can approximate this integral by a stationary phase approximation. And deduce that the value of q at which this amplitude is sharply peaked in the classical limit is simply the derivative of the iconal phase with respect to the impact parameter. So our efforts have been repaid because now that we have calculated the leading order and the subleading order iconal phase, we can just take the derivative with respect to B and calculate and obtain the classical momentum transfer. And the classical momentum transfer, okay, is equivalent to the deflection angle, right? Because this very complicated trigonometry identity. So Q is equal to 2P, the sine of theta half. So now that we have Q, we have theta, if you want. It was the objective we set out to achieve. And now, before concluding, the very last thing is we are also in a position to go back as to why this infrared divergence in the leading iconal was actually not a problem. And the reason is that to go from the iconal to the observable thing, so really by how much the objects deflect in the process, we have to take this B derivative, which means that, okay, the B derivative is going to kill the 1 over epsilon and leave behind a well-defined classical result that maybe we can start writing down and discussing in the next lecture. So I think this is it for now. So if there are no questions, everybody is... Yeah. Well, there were two limits, you remember. One of them is h bar over m being very small than gm, and the other one is that both are much smaller than b. So this is the classical limit, and this is the PM limit. Now, of course, the two imply that B is very big. In particular, BM is very big compared to H bar. But I would say that conceptually, the classical limit is this one. In principle, does not rely on being in this large B. The problem is that if you try to do some head-on collision of black holes, it's going to be a very hard calculation because gravity becomes very strong, and then we have to use computers. That's actually what our colleagues in numerical relativity do, right? I mean, they arrive until the very end of the merger in which the two things are still classical. They don't use any H bars, but I mean, but B is basically zero at that point because it's... That's right. That's right. So the reason why we are extracting the next leading correction to the phase and therefore to the deflection angle from a loop diagram is that our usual intuition about what is quantum is a bit wrong in this regime because we are going beyond the regime of perturbation theory. So usually we write down our perturbative expansion and we say loop diagrams are suppressed. But the fact is loop diagrams are suppressed by gm squared over h bar. If you think about electrodynamics, it's even clearer, right? E squared divided by h bar c is the phi structure constant. This is literally your perturbative parameter, right? So this has a 1 over h bar in front. So you can only trust the fact that the one loop diagram is small with respect to the tree level when h bar is large, or e squared over h bar c, more precisely, is a small parameter, right? Here it's exactly what is not correct. So we have to first resum it, and then we can interpret things in the right way. The right way to think about it in this case is that what is sitting in the exponent, which is large because it multiplies this parameter here, is classical. And things that are further suppressed, instead, things that sit here, for instance, will not have this gm squared over m squared over h bar enhancement. It might be, say, of order h bar over mb, for instance. Those guys are actually quantum. But it's true that there's a bit of reshuffling from this writing, which are more used to this exponentiated form. Okay. If there are no further questions, I think we can enjoy the break and then come back for the next lecture.